Bueno, con esa preciosa introducción me lo pone muy fácil el profesor Maiz para anunciar su conferencia Nanociencia y nanotecnología, promesa, realidad y desafío. La charla del profesor Maiz será introducida por Pedro Luis Arias, catedrático de Ingeniería de la Universidad del País Vasco y ahora viceconsejero de Universidades e Investigación.
Arratsaldeon, buenas tardes. En primer lugar, agradecer esta oportunidad de presentar a José Maiz y, por supuesto, no solamente a todas las personas que han acudido, sino a aquellas que han hecho posible este congreso. José Maiz tiene sus orígenes en el barrio del Antiguo. Yo creo que administrativamente no cabe duda de que eso forma parte de la ciudad de San Sebastián, aunque yo he oído a mucha gente del Antiguo decir que baja a San Sebastián cuando sale de casa. En cualquier caso, ciertamente yo creo que ese origen marca profundamente, ya que no en vano hay que reconocer que es un barrio que al crecer ha sido capaz de imponer como nombre a esa ampliación una contradicción in terminis, porque he oído hablar de Antiguo Berri. Entre 1971 y 1976, José Antonio estudió Ciencias Físicas en lo que hoy se conoce como Tecnum, centro de la Universidad de Navarra, con sede en esta ciudad de San Sebastián. Y en la actualidad mantiene una estrecha colaboración con su alma mater, ya que desde el año 2004 es miembro del patronato del CEIT, el centro de investigaciones que funciona allí mismo. Y también desde 2008 forma parte del Consejo Asesor, del Board of Advisors del CIC nanoGUNE. Después de estudiar Ciencias Físicas, en 1984 consiguió una beca Fulbright y con ella se trasladó a Estados Unidos para completar su formación. Sería en la Universidad Estatal de Ohio, en Ohio State University, donde primero en 1980 obtuvo el título de Master of Science y en 1983 el doctorado, ambos en Ingeniería Eléctrica. Bueno, pues sería a partir de 1983, recién terminado su doctorado, cuando comienza a trabajar en Intel. Esa empresa que ha sido uno de los grandes líderes en la revolución de la electrónica digital, fabricando los microprocesadores que han permitido pues, que hoy en día ordenadores como el suyo, el que va a utilizar en esta presentación, sean de uso común y además hayan revolucionado tantas facetas de nuestra vida. Estos microprocesadores han sido cada vez más potentes a través de diversas generaciones con dispositivos de tamaños que van acercándose a los límites físicos del silicio. Bueno, pues José Antonio ha sido uno de los protagonistas de esta apasionante historia, explorando esos límites que afectan al tamaño y a la fiabilidad de esas sucesivas generaciones de microprocesadores, aprovechando todas las oportunidades que ha ido encontrando en el camino y resolviendo multitud de problemas, y fruto de ello pues son sus publicaciones, patentes, su presencia en numerosos comités, paneles de expertos. Bueno, toda esta tarea ha merecido muchos reconocimientos. Destaco aquí que desde el año 2002 es Intel Fellow y dentro de esa organización, dentro de Intel, es en la actualidad el director de calidad y fiabilidad de tecnologías lógicas. Se preguntaba desde la audiencia hace no mucho tiempo el impacto económico de la nanotecnología. En otros ámbitos quizá sea una evaluación difícil, pero en el ámbito de la que se empezó a llamar microelectrónica y probablemente hoy debería llamarse más propiamente nanoelectrónica, pues el impacto económico es ya indudable y de una importancia extraordinaria. Como ejemplo, les diré que nuestro ponente, José Antonio, empezó a trabajar en Intel preparando una primera generación de componentes fabricados en la escala del micrómetro, es decir, de los 1000 nanómetros, y en la actualidad se dedica a supervisar el desarrollo de tecnologías que andan entre los 15 y los 22 nanómetros, es decir, en esa escala de unas macromoléculas de un tamaño razonable, según nos explicaba el anterior ponente Juan. Pues con ustedes, José Antonio Maiz, y su presentación, donde a través de su experiencia nos va a transmitir cómo la nanotecnología es una de las herramientas fundamentales que nos van a permitir construir ese futuro en el que vamos a tener que vivir y además vamos a tener oportunidades en las que vivir siga siendo enormemente interesante. Eskerrik asko.
Muchas gracias, Pedro Luis. Bueno, lehendabizi, arratsaldeon, jaun Andreok, y muchas gracias a todos ustedes por venir aquí, por tomarse el tiempo de escucharnos. Y quiero dar las gracias también a la organización de Atom by Atom por invitarme a dar esta presentación. Es como siempre un placer el venir a San Sebastián. Ladies and gentlemen, I wanted to thank you for your presence today. And I would like to give my appreciation also to the Atom by Atom organization for inviting me to present. It is a great honor for me to do so, especially in the presence of three great names of nanoscience, Professors Firth, Kroto, and Rohrer, who have been awarded Nobel Prizes for their accomplishments. And from a practical side, it's a great thing to have them here too, because if you ask me a very tough question, then I can always refer it to them. So with that intro, I would like to basically discuss some of the challenges, some of the situation in nanotechnology the way I see it. And I will start with a couple of quotes that I have found inspiring over time, and it looks like many others have found them too, so you probably are getting fed up of listening to things about Feynman, but that's my first one, and so let me go for it.
There is plenty of room at the bottom. I am telling you what could be done. We are not doing it simply because we haven't yet gotten around to it. There may even be an economic point to this business of making things very small. Richard Feynman, 1965 Nobel Prize in Physics.
And as it has been mentioned by others, this was a full 50 years ago, so he was truly a visionary.
Human health has always been determined on the nanometer scale. This is where the structure and properties of the machines of life work in every one of the cells in every living thing. The practical impact of nanoscience in human health will be huge. Richard Smalley, 1996 Chemistry Nobel Laureate.
So Dr. Smalley, who along with Dr. Kroto received the Nobel Prize in 1996, tells us, reminds us of the impact on human health. This is going to be a major theme that I expect we will be listening about or hearing about in the next years. So the question over here is, what is it? What is that we are talking about? And you have seen multiple speakers trying to give you different versions of what this thing is, and I'm going to try that too. So at the risk of repeating things a little bit, I'll say that nanotechnology and nanoscience is basically refers to unusual properties when you go into the nanoscale. And this example is a gold nanoparticle that strongly scatters light and absorbs light when you illuminate it with the correct wavelength. But it is also light and strong materials, like in this example of a proposed artificial muscle for robots. It is made with an aerogel of carbon nanotubes, and it is barely more dense than air, as you can see, but it's 30 times stronger than a natural muscle. Or it could be zero-valence iron nanoparticles that have been proposed for remediation of contaminated sites, and I'm going to be discussing briefly too. Or it could be the wonder of self-assembly, as in when a seed becomes a plant. And in trying to understand that is a major challenge for nanoscience. I like to keep this plant on top of my desk for the last 4 years or so to remind me of it. And it's very generous with me because it provides me beautiful flowers, self-assembled flowers, in exchange of a little bit of water and a little bit of coffee to perk it up once in a while. So whenever there is a new field, a new revolution, it is good to look at the money. Where is the money? Where is it going? Where is it coming? What is producing, right? And this is a graph that shows the investment worldwide in nanotechnology from public sources. And you can see that it has been steadily increasing over the last 10 years. You can also see that the investment from the US and the European Union and Japan early in the decade was about the same. And that the Japanese investment has been plateauing a little bit lately. But there is another very interesting feature, is that in 2007, the category of others has had a huge jump. This is primarily emerging economies trying to, or realizing that they have to invest in this if they want to benefit of get the benefits And this is primarily China, who has invested in the range of 350 million in the last year. The other thing is, how do you measure the impact of these things? Well, there are many ways of looking at it. In these early stages, looking at patents may be an educational thing. If you look at the patents, the ramp, the number of patents per year is growing exponentially. The US Patent Office tends to be the most successful in registering and issuing patents on this matter. The European Union comes somewhat behind, and the Japanese seems to be plateauing. Now, that doesn't mean that the Japanese companies are not active. I think that it only means that they have chosen to patent either in Europe or in the US rather than in the Japanese office. So self-assembled humans are a very curious creatures. So I would like to go with that self-assembly concept. Just go ahead and explore a little bit. The first thing I would like to mention is that nature uses nanoscience or nanotechnology, and uses it in a big, big way. All of us are nanotechnology. And if you look at how DNA, and this concept has been repeated a number of times in these days, the directed self-assembly of DNA is capable of producing wonders. It produces molecules that are proteins that are extraordinarily critical to life, like hemoglobin, so that you can breathe. It can self-assemble a brain, a human brain, with all this wonder, and a whole child. And notice that it makes it very reliably. It never puts the nose where the ear should be, or the other way around. So there is something very precise in the way that this thing gets done. Let me give you another example of how nature uses nanotechnology. Let's take the spider that spends its time in our backyard. And the spider web is made out of silk, of a type of silk that is a wonderful nanotechnology material. It's made out of proteins that interlock with each other. And this remarkable material, This remarkable material is stronger. It has a tensile strength that is higher than steel typically, okay, and it can absorb 25 times more energy. What that means, and somebody has estimated that if you were to make a rope out of this silk, out of this spider silk, that is 1 kilometer long and 30 centimeters in diameter, you should be able to stop a 747-400 in full flight within 300 meters and 1 second. It is that strong, okay? The more remarkable thing is that the spider makes this material in a totally benign way. It does it without the need of big factories. It does it without massive amounts of electricity that result in global warming, or without producing contaminating chemicals that are bad for the environment. So there is a lot that we have to learn about. So with that, let's look at some promising examples that we have seen emerging in the nanoscience and the nanotechnology world. The first one I wanted to bring up is the remediation of contaminated sites. Because of our carelessness in industrial processes, typically, what we have is many sites in the world that are heavily contaminated with things like organic solvents that are known carcinogens, or with things that are pesticides that are very long-lived, like lindane. Or it could be that we have massive amounts of fertilizer from runoff of large agricultural operations. It could also be real toxic metals that result from industrial processes. And it has been shown that these iron nanoparticles, the zero-valence iron nanoparticles, are effective in neutralizing many of these by oxidizing. And in oxidizing, they degrade some of those materials. And the thing that is interesting is that they are very cheap to make, and they are very benign because the iron is already in the system, it's already in the ground. And this can be achieved with concentrations of iron that are not different than the iron that already exists in the environment in ionic form. So you may wonder, why am I talking about? Why do I need to throw iron nanoparticles? Why don't I just throw nuts at the place, right? It's iron, right? But see, the iron nanoparticles have a surface-to-volume ratio that is 4 million times larger than the nut. And chemical reactions depend on the surface area. They don't depend on the volume. So for the same amount of volume, I can get a 4 million times increase in the efficiency of the reaction. That's what makes them interesting. I wanted to review another case example, which is the gold nanoparticle that some people in some forms has referred to. that I consider extraordinarily interesting. And I heard that somebody over here in San Sebastian actually is working on this area, so this is great. Gold nanoparticles can be made in the form of spheres, nanorods, nanoshells, all kinds of things. And they are easy and inexpensive to make. But they have other properties. Like I indicated before, these nanoparticles of gold strongly scatter and absorb light if it is illuminated with the correct wavelength. And these properties are going to be useful. And this is because of a surface plasmon resonance property of these nanoparticles. The thing that is interesting about these nanoparticles is that they can be easily bioconjugated, which basically means, in layman's terms, that you can attach to this nanoparticle a protein fairly easily. In this specific cartoon, what I have it is an example of attaching it to an antibody of an EGFR, which is an epithelial growth factor receptor. And you'll see in a minute why I'm interested in that. It turns out that certain cancer cells in humans, specifically the skin cancer type of cells, like the human squamous cell carcinoma and the human oral carcinoma, these types of cells overexpress a protein called epithelial growth factor receptor in their membrane. They have lots of it in their membrane. So, of course, you see where I'm headed now. If I have that cell that overexpresses that protein and I have this gold bioconjugated to the antibody of that protein, I can selectively, or fairly selectively, attach the nanoparticle to the cell. Now, why would I want to do that? Well, because it helps me on diagnostics. Look at the pictures in the right. The two columns in the right are cancerous cells, and I want to be able to distinguish a cancerous cell from one that is not. In those cases in the right, in the two columns in the right, the high density of nanoparticles that have been attached to the membrane produces a scattering of the light in a way that clearly delineates those cells. In the case of the healthy tissue in the left, the nanoparticles are dispersed because they don't have a place to attach themselves, and there is no definition. So it allows you in diagnostics. Another way that it helps you with diagnostics and location is in visualization. It turns out that the infrared light that is of interest can penetrate soft tissue for about 10 centimeters or so. So effectively, by just shining infrared light or the light frequency over here, you could visualize the tumor much better in terms of localizing it where it is in case that you want to do something about it in a physical term afterwards. And you can do that in a totally non-invasive way by just shining on it. But there's more on this, right? We said that in addition to scattering the light, it absorbs the light. So since we have now large concentrations of nanoparticles attached to the cell, I can apply a higher intensity of light, and then what I can do is increase selectively the temperature of those nanoparticles. The cells that are cancerous are going to absorb a lot more because we are going to have more nanoparticles in them. The temperature, the red graph over there, will increase dramatically, and it will kill the cell. While in the healthy tissue, by having fewer nanoparticles, will increase only slightly the temperature. So this is an option of treatment. Of course, we have to keep in mind over here what Dr. Rohrer told me is how do you get rid of the nanoparticles afterwards? And it is my understanding that gold nanoparticles are non-toxic to humans and that they get released fairly easily afterwards, but I have no knowledge to prove myself. I wanted to go now a little bit into the nanoelectronics part. And the nanoelectronics, as you will see in a minute, is like a madman's race to decrease dimensions. And we are always looking for better materials, novel nano devices, efficient interconnects, and more effective architectures. And as I said before, we have come a long way from the times of the ENIAC, that was a computer made with vacuum tubes, to today's devices. We have an improvement, a reduction in size that is of the order of more than 100 million. And so is the improvement in efficiency, is more than 100 million at a much reduced cost. So those are big numbers. And what those enable are fantastic things that we kind of take for granted today, like fairly accurate weather predictions, for example, or the ability to communicate with anywhere in the world, whether it is by audio or by video, or have access to data anytime, anywhere, in a hospital or in any other environment. It also, the supercomputers allow us to help with drug development or oil exploration or things of the sort. And then there is the impact that this thing is having in social terms, not just in terms of hardware and what you can do, but how people relate to each other, whether it is through the internet, through Facebook, through MySpace or Wikipedia or whatever other. There is an infinite array of things that are coming up that are impacting. So let's discuss briefly how we came here. In order to come here, in microelectronics, we keep scaling down the dimensions of our transistors so we can fit more and get more functionality. If you look at the last 20 years, we have improved the performance about 100,000 times. And what this graph shows is the technologies introduced. This is Intel data, and you can see that with a very regular cadence of 2 years, we have been successful in introducing new technologies. The numbers there correspond to the nanometer reference nanometer number of the technology, which approximates the gate dimension. But after we spent 30 seconds congratulating ourselves for this magnificent graph, we immediately draw a line a little bit farther and see that in the next 10 years, we are going to have to come into the single-digit nanometer. And the question is, how are we going to do that? And obviously, all this huge brain power that is in this room perhaps will help us, right? So in order to discuss a little bit that, I wanted to start with this description of how a transistor looks today. In the left is a transistor of our 45 nanometer technology generation, which is, about the size, or perhaps could fit if you try to push it a little bit hard, inside an HIV virus. It's of the same types of dimensions. And the question is, how are we going to move forward? If we want something new, what do you do in a city when you don't have enough space to build? You start building a high-rise. So we are thinking into doing, for example, tri-gate transistors, where instead of building in a planar semiconductor, we are going to build walls of semiconductors so that we can take advantage of the wall, the top, the side, and the both sides in order to get both. A larger semiconductor conduction, right? Or we can say we can go to better materials. We have known that 3,5 materials like indium antimonide or indium gallium arsenide are better semiconductor materials than silicon. The question is, how can we use that? Because those materials tend to be expensive and difficult to work with. So let me show you some things. By the way, I'm calling these things somewhat evolutionary. People that work on these would basically give me a real hard time if I put somewhat evolutionary here, because these are very, very difficult technologies. But what they share is that they use known materials, and they use concepts that are like a field effect transistor, which is what we are using today. So let me give you the example of the 3.5, because I think it's most interesting about how nanotechnology plays a role here. I have the indium gallium arsenide over there, which is a very, very nice material to make devices with, and is typically referred in the, in the technology groups as InGaAs. And this is very nice material, but this material is expensive, and it's very difficult to make wafers with and to work with and so on. And what we like to work is with silicon. Silicon is nice. We have a good infrastructure. We can do things cheap. We can make them with high yield. So I would like to put the indium gallium arsenide on top of the silicon and process it like that way. What happens? What happens is that the lattice constants of these two semiconductors are very different. So if I put the InGaAs on top of the silicon, it's massively defective, and my devices won't work. So I take advantage of nanotechnology, and I'm going to say, I'm going to go, if you look at the bottom to this cartoon over here, you have that the silicon substrate has a certain lattice constant of about 5.4 angstrom, and I need to move to that layer that says InGaAs channel 30 nanometers that has 5.9. So I'm going to use nanotechnology by going nanometer to by nanometer. I'm going to make that transition in a way that not only transition the lattice constant, but do it in a way that I trap the defects along the way. So that when I arrive at the true channel that I'm interested on, I have a good quality material. And if you do this thing correctly, you can get a beautiful material of InGaAs, which is the one that is referred over here as InGaAs quantum well. And this transmission electron microscope, you see that is very much defect-free. And if you can do that and you can build your devices, you get rewarded by wonderful performance. Like this is a graph that shows you the maximum frequency of operation in the left as a function of the power dissipation in the x-axis. Power is something that we are always fighting with in electronics, okay? So if you want to say, I have a certain power budget and I need to look at this graph empirically, I would say that I can achieve maybe 3 to 4x improvement in performance by using InGaAs with respect to silicon. Or if I want to operate at a certain frequency by looking at the graph horizontally, I can see that I can reduce 10x the power consumption while operating at the same frequency. So these are some wonderful things that we are looking at this point. Now, beyond those things that I have called somewhat evolutionary, there is other sets of things that people have been proposing that are a lot more exotic. You can see, for example, in the top center that I have carbon nanotubes, and in the bottom left, perhaps nanowires. Transistors have been built with both, with nanotubes and nanowires. However, these guys have a tremendous problem, and the problem is that I need to be able to locate them properly in the right location and in a predictable manner in order for them to be useful. Just imagine that what we make today in a chip is we take a centimeter square of silicon and we put 1,000 million transistors on it. All of them have to work. Not most of them, all of them have to work. So if I do this thing with nanotubes, I should be able to put the nanotubes exactly in the place and every time in a correct manner, and we do not know, we absolutely don't know how to do that. In the top right, there is graphene. Graphene is a wonderful material in terms of some of the properties of mobility that it has. However, the band gap is not right when you use a full sheet. We do not know how to change the band gap. We do not know how to make contacts with it. So these devices, if they ever become useful, it will take a long, long time, and it won't happen until we resolve those problems. In the bottom right, perhaps the molecular electronics is the most desirable one of them all. If I can make a transistor that is a molecule, that would be great in terms of dimensions and so on. However, when I make a metallic contact to it, I typically destroy the molecule. So my suspicion is that molecular electronics won't come in a big way, for performance at least, until we make some sort of self-assembly contact to it. In the center, I have something that we are benefiting from Professor Firth's discovery, and is the perpendicular spin torque transfer ramp that I'm going to be discussing in a minute. This is a memory device. It's a way to store information. It's something that is being looked at as a substitute to this pen drive that you have in your pocket, perhaps, or to that MP3 player that you carry along. Okay? As a memory device, this is based on the giant magnetoresistance effect discovered by Dr. Firth and Dr. Grumber, and for which they got the Nobel Prize. And to keep it very simple, you can look at this layer that I'm calling PL that has a magnetized direction up, in the way that this cartoon explains it. And then you have a free layer that can have the magnetization either up or down, separated by a non-magnetic layer. And then the interesting thing is that if you have both aligned in the same direction, both magnetizations aligned in the same direction, the resistance of the whole stack is low. If you have the magnetization in opposite directions, the resistance of the stack is high. So you can store ones or zeros depending on how you align those. And those can be programmed electrically. So this thing is interesting. Whether this thing will get to substitute the present flash memories, for example, it remains to be seen, but there is a tremendous amount of work going on it. Of course, there is another aspect of it that was a great success of nanotechnology, which is the hard disk drives that are used today, Dr. Firth's invention or discovery of giant magnetoresistance. The amount of those devices work serially, and the giant magnetoresistance is used primarily to detect, as a detector of magnetic field. And I can tell you a story about it. This summer, my daughter came home and told me that, or let me know that the 300 gigabyte hard drive that I had given to her when she went to college was getting full. And I said, how could it be possible that you have filled up 300 gigabyte disk? And he says, yes, it's full. And I said, well, as a father that I am, the first thing I did is I went to the store and I'm going to buy her a bigger one. And I went to the store and I found a beautiful 1.5 terabyte hard disk, right? And to my amazement, this device was kind of nice and small and self-contained. And I looked at the price and it was $135 US dollars. And I said, that's $1 for 10 gigabytes. So I said, I need to, when I go to San Sebastian, I'm going to personally thank Dr. Firth for saving me some money. I mean, this is 1.5 terabytes. It's a remarkably large amount of storage. One thing I want to bring your attention when we analyze, I'm very often asked, well, how about graphene? How about nanotubes? Why don't we make transistors this way? Why don't we make transistors that way? Well, you have to keep some criteria about how you separate a little bit what is possible from what is useful. All right? So there are two things that are necessary when you have a novel device. The first thing is, can I make it? And if I assume or give you the benefit of the doubt that you can make it, then the question is it useful? Like in this graph, for example, what I have is a metric that we use very often in electronic devices, which is energy delay product, which basically means how much energy does it take to make a switch, a transistor switch, multiplied by the amount of time that it takes the signal to propagate. That's a basic figure of merit. So to have a number like that is low is very important. Now, the large number of diamonds over there is silicon technology. If I make a carbon nanotube, those are the circles. So when I compare the circles to the diamonds, at least with the present type of approaches, okay, the nanotubes don't seem to be any better than silicon. So I may go through a huge difficulty making the nanotubes. It's not clear that they would be useful to me. However, the 3.5 devices, in this case indium antimonide, has a substantially lower product, almost by 2 orders of magnitude, than silicon. So that's a material that I'm very interested on. I'm giving you a criteria of how sometimes we direct or where we put our attention. So when you have these types of devices, you have to indicate that the outcome is uncertain, because in order to be useful, they have to outperform silicon in a big way. They need to be scalable so it allows us to keep going to smaller dimensions, and they have to be able to be integrated with yield and reliability. So those things have to be kept in mind before we move forward, at least for use. Another material that is most interesting that was referred to, I think, yesterday was the organic light emitting diodes. I think that Professor Mendez indicated that a huge inefficiency in illumination, for example, and the organic materials that emit light are being proposed as a much more efficient and much less expensive potential source of illumination, like you are seeing over there in a mock-up from General Electric. And also, it can be used in flexible displays or to display information, like in this concept slide from the Fraunhofer, where you can display the information that you want to get access to in your glasses. Okay?
Hello, Dave. You're looking well today.
So what I wanted to show you a little bit, or give a comment about the computer architecture and the von Neumann architecture that we are using today. This type of computer architecture has been used since the early days until today. We have fancier devices, but the architecture hasn't changed one bit. What I wanted to call your attention is to the fact that nature does it in a different way. Nature builds a brain, and in fact is redundant, is low power, is self-assembled. You don't need machines to assemble it. It has the ability of abstraction and self-consciousness. And today we are at a stage we cannot replicate the neural network of a fly. So we have a lot to learn in this dimension. The other question that I get very often asked is, how long will it take? Will we have factories doing nanotechnology in the, all full with nanotechnology in the next 5 years? How about 10? Well, I like to answer that question primarily with a description of what happened with the electronic industry. The transistor was invented in 1947. The transistor radio was in 1954, 7 years later. 20-some years later came the personal computer, and eventually enough technology got built up in various aspects of it to allow a huge explosion of applications. Because suddenly the whole thing exploded, and we have the internet and the iPhone, and we can communicate with everybody. We have the GPSs, social networks, and the whole thing. So typically these things, what happen is that it takes some time until they reach critical mass, and then suddenly the whole thing blooms. Okay? So what do we need to do in order to make that nano a reality? I think that the most important people is in the top left. We need to invest in people. We need to have people that are extraordinarily well prepared so that they can recognize things, discover things, and take advantage of things. In the top right is how do you make something useful out of it? You need to have a very strong industry to university alliance, because once you have that discovery, once you have that opportunity, we need to be able to take advantage of it in a product. And the bottom ones relate to policy and to development of a culture of entrepreneurship where perhaps risk-taking is valued and where failure in those risk-taking doesn't necessarily destroy your career, which is probably what I best understand the secret of some of the excellent places of innovation like Silicon Valley. So I want to start closing this talk by indicating that to you that the nano revolution has clearly started, okay, and I want to send you home with two messages. The first one is that the promise will be realized. This is for real, and it will happen. And it will happen in a way that is much, much bigger than anything any one of us has ever imagined. The applications will be much different and much bigger. We just have to keep working at it. But it also will take time. I'm totally of the opinion of Dr. Smiley that the convergence with bioscience will be huge. I think that there is tremendous amount that we can learn from and get inspiration from living organisms, and concentrating, understanding and mastering the self-assembly method is key. So you can ask, how do I know that? Well, I know that because you have already done it, okay? If you think of it, your mother did not build your brain, and neither did you. It just built itself. Now, that's a remarkable statement, that the brain built itself, okay? So, and all these things happened while she was enjoying a walk, perhaps, or while you were playing in the playground. So it didn't feel like work, really. It felt like play. All right? So with this message, I want to ask you to go ahead and, with full energy, go invent, discover, get energized and excited about what is possible. I wanted to thank a large number of collaborators that helped me putting together some of this information. And I wanted to thank you. So I'm ready for your questions.
Tenemos tiempo para un par de preguntas. It has been so impressive that nobody... Okay, yeah.
Go ahead.
There's the microphone here. El micrófono.
It's really impressive how it moves on and how you sold it. I mean, you didn't oversell it. I just have one problem, and that's with the university-industrial relationship, you see. We are already now a little bit in a situation where we lose the scientific freedom. And the scientific freedom will be lost much more with every cooperation we make. That doesn't mean that you should not make cooperation, but we simply have to be very careful what we are doing. Take my example. I worked for IBM. But I had the freedom to do something which IBM never would have done if they only would have thought on their own problems, you see. And so
let me make a comment about that. I think that you are exactly correct, and I don't think that what I said contradicts that. And I'll tell you why. I think that when you look at the whole industry to university collaboration and how governments play with this whole government funding looks into that, this is not whether I do pure science for discovery's sake or whether I do practical applied science for use. These two are necessary. All I'm saying is that you cannot go one way completely or the other way. I think that we have a lot of the situation I'm trying to correct, specifically I think in the Basque Country effectively, is that this interaction between the industry and the university is kind of very weak, I think. I don't think I'm saying something incorrect here. So by strengthening that, that doesn't mean that you have to eliminate the freedom of certain sectors to investigate and research on basics. It means that there has to be somebody thinking and developing a path so that when somebody discovers something good or something is pursued, in a way that is directed research in order to accomplish something, there is a path for a quick implementation in industry. That's what is going to lead to basically increase the standard of living of people, is going to create jobs, and it's going to effectively allow you to get enough resources to continue funding the basic research, because otherwise the basic research is going to dry up. So it's somehow, I don't know if you agree or not, but it's a tricky play. It's a tricky play, but I think that those two things have to be complementary.
Okay, there's otra pregunta.
I think I follow the same question. I would like to know how big is the research and development department in your company, for example?
Well, in our company, we do not do fundamental research. Let me start like that. We depend, and we like very much universities to do fundamental research. We benefit from it. We sometimes grant them to do things like that. In our company, inside, what I like to say is that we do not do research and development. What we do is development and research, which basically means I know that in 2013 I have to have a 16 nanometer technology generation out the door. Do I have problems? About 5 million of them, right? So what we are going to do is we are going to do research internally, we are going to fund universities, we are going to still borrow, whatever. Try to understand how to solve the problems that we need to solve. So in that sense, it's a very directed. Internally in the company, it's very directed. But we try to collaborate very closely with universities that do a lot more basic research.
¿Alguna otra pregunta? Okay, thank you very much for Yeah, there is another one.
Yeah, there was one more question. Yeah, thank you for your beautiful lecture. I'm a bit surprised at what you said about gallium arsenide. So I'm not as young as I was. So a quarter century ago, I started working on gallium arsenide, and then it was known as the material. It's the material of the future and always will be. And now you're telling us that there might now the future really existing for the 3-5 materials?
Well, I think that the 3-5 materials are being used today, but they are being used in niche applications. You have companies like DIPC or like companies like TriQuint, one in Oregon, one in New Jersey, that are very active in making, for example, power amplifiers for wireless devices, right? Like those power amplifiers are typically 3-5. Now, 3-5s have not made it into regular computers for computing purposes because they tend to be too expensive and because the wafers are too complicated to handle and too expensive themselves. So the thing that is going to enable the 3-5 is the ability to put them in silicon in that defect-free form. If you can put a 3-5 material on silicon and make it defect-free, then you can use the whole infrastructure of silicon. And if you can use that infrastructure to make it cheap, to make it inexpensive, and to ensure that you can manipulate it with equipment that produces good yield and so on, but make the devices in 3-5, like in InGaAs, like in indium gallium arsenide or indium antimonide or things of that sort, I think that that opens a huge range of possibilities. So my short answer is yes, I think there is life for 3-5s. And I think that it's hard to determine when, but I think that eventually we'll hit the market in a bigger way than they are today.
Thank you.
Well, okay. Muchísimas gracias, José Antonio. Thank you very much for your presentation.